Okay, so today we're going to cover mixed ANOVA. This is going to be the last type of ANOVA that we're going to talk about in this class. So the mixed ANOVA, I was a bit worried about teaching this because I had never taught mixed ANOVA to undergraduates before. And I thought, ooh. But preparing for today, I'm not too worried. I think you guys are going to be able to get it. Inshallah. Okay, so mixed ANOVA. Come on. So far, we've talked about ANOVA. When I say ANOVA without saying like repeated measures or mixed, I mean a non-repeated measures ANOVA. Just a plain old ANOVA. Okay, so for our non-repeated measures ANOVAs, we talked about each observation was independent. A couple classes ago, that was one of the assumptions that I said, right? We have independent observations, and we'll make a special exception to this. What is the special exception? I haven't pointed it out, but we made one. When do we not have all of our observations being independent? When we have something like a paired t-test. What's the ANOVA equivalent of a paired t-test? Repeated measures. Repeated measures ANOVA. So for non-repeated measures ANOVAs, each observation is independent. We have one participant, or one subject, for each observation that we have. The means that we are getting for different combinations of levels for the different factors, or for all of the conditions, each of those means comes from different subjects. For our repeated measures ANOVA, on the other hand, not every observation is independent. Some things are independent. Like, okay, I'm going to randomly pick people. Okay, you're going to be in it, you're going to be in it. So I'm picking people independently of one another, but then I'm measuring them multiple times. So this is the one exception that we're sort of making to this general rule of independent observations. Now, instead of having one participant for each observation, we have one participant providing multiple observations, right? We have one observation from each participant for each condition. The condition is just the combinations of all of the different levels of all of the different factors, right? And the means for these different combinations of levels come from the same subjects, right? And the same subjects in one group as you do in the other group, right? Different conditions, but same group of people. Okay, so we have our regular old ANOVA, one participant for each observation, and our repeated measures of ANOVA, where we have one participant for several observations. Now we're going to get into a mixed ANOVA. Mixed ANOVA. What does mixed mean?
Repeated and non-repeated.
Mixed means if we're talking about ANOVAs and we have like repeated and non-repeated, then maybe mixed means we have some of the repeated and some of the non-repeated, right? We're mixing those two things together. That's exactly right. So with a mixed ANOVA, we have part of it is just like a non-repeated measures ANOVA. So means for some of the different combinations of levels of the factors of interest are going to come from different subjects. And part of it's going to be like a repeated measures where the means for the different combinations are coming from the same subjects. So you will have some of the factors measured between subjects, something like sex. You have different groups of subjects in a male group than you do from a female group. Or major. You have a different group of people that are history majors and psychology majors, right? So we will have some of our groups, sex, major, ethnicity, socioeconomic status, those will be like the non-repeated measures ANOVA. And other things, maybe like Q, or list, or what caption you see. those would be like repeated measures ANOVA. Okay, so let's take a quick review over the last class's data. So we were talking about a memory experiment. Yeah?
What about interactions?
We will get to interactions.
No, we will calculate both of them or repeated ANOVA?
I'm sorry, I don't understand the question.
Interactions that we will cover. Will be dependent non-repeated ANOVA or repeated?
Both. Both. It's mixed. Don't worry. Hopefully, I present it in a way, or I will present it in a way that will make sense. Okay, so last class we were talking about a memory experiment, right? Where we give people lists of words, and we are calculating some score, which is our dependent variable, right? Their score on the test after they've tried to learn the list of words. And we have different factors. And one of the factors we had was Q. Whether or not they got cues to help them remember words on the list, or they didn't get a cue to help them remember. Our second factor, our second independent variable, was list, which was the type of words that were on the list, whether they were abstract words or concrete words. Now, for this last class, we analyzed it both in the normal ANOVA way and also in the repeated measures ANOVA way to contrast the difference. But the way I set this up really was as a repeated measures type of thing. So these independent variables vary within subjects, right? So one subject got a cue for one of the lists and no cue for another list. And each subject got a list of concrete words and a list of non-concrete words, abstract words, right? So those factors are varying within a subject. Each subject is getting each level of those and each combination of levels of those. So those independent variables vary within subjects. And because of this, this is why we use the repeated measures design to pull out that variability that was related to subjects and throw it out. Just get rid of it. So this decreased the size of our error for the individual tests that we were doing. Okay, so for today's class, we're going to throw one more independent variable in here. Sex. Male or female. This type of independent variable doesn't vary within subjects, right? Actually, I guess you could have something like this. You could have someone say, okay, imagine that you are a female. Now we'll learn this list of words. Or imagine that you are a male and do that. That's sort of odd. Not many people do that. So we're just going to talk about sex in the normal sense. It's something that's varying between subjects, right? Now, when we had something that varied between subjects, what type of ANOVA did we use?
Non-repeated.
The non-repeated measures ANOVA, right? So we have some variables in here that we use the repeated measures ANOVA to analyze, and we have some variables in here that in the past we have used the non-repeated measures ANOVA to analyze. So let's compare the repeated measures and non-repeated measures before moving on to mixed. So let's do a 2x2 ANOVA first for Q and list, right? Now when we do the 2x2 ANOVA, without the repeated measures part, I haven't specified an error term with subject nested as anything. So when I don't specify this, it basically treats the data as if each observation comes from a different subject. Because it doesn't know, you have to tell it. So if we do that, we get a sum of squares for Q, we get a sum of squares for list, we get a sum of squares for the interaction between Q and list, and we have sum of squares for our error, right? And how many error terms do we have?
3 and 1.
1. We have one error term here, right? We use this same error term
4.
for each of the tests, right? So, for our 2x2 ANOVA, this is the ANOVA that's appropriate for a between subjects design, and we have one error term. Now this error term is based on variance between subjects. In fact, in the between subjects, the only things that are varied are between subjects. So this error term has to come from between subjects variability. Okay? So we have one error term that's based on variations between the subjects. And we use this single error to test all of the effects and the interactions that we might have. If we had more factors, hue, list, let's say color, we colored some of the words, and we made some different fonts. We had color and font. Well, we would have hue and list and color and font and hue list, hue color, hue font, list font, list color, all of those different combinations, right? But we would still just have this single error term that we would use to compare all of these mean squares against. All right. Now, for our 2x2 repeated measures ANOVA, things got a little bit more complicated. So, again, I have basically the same initial part as I did last time. Scores is a function of Q and list. Scores is a function of Q and list. The difference now is I've added in an error term. So the error is going to be subjects nested within Q and list. So we do this and we get data that looks like this. And now all of a sudden, instead of having just one error term, we have a bunch of error terms, right? Now, this type of ANOVA is appropriate for a within subjects design or a repeated measures design, right? Now, even though we have multiple error terms, notice that each of these error terms is based on between subjects variance, right? That's where this interaction comes in. The interaction of subject with list, right? The subject part is between subjects. So even though list is just within subjects, the error, which is basically the subject by list interaction, this is something that is between subjects. We have a different subject affected differently by list, right? So these differences are differences between subjects. So let me go back and try to make this very clear. So here we have one error term. And this error term is based on variability between subjects. Here we have multiple error terms. Each one of these is different, but each one of these is also based on between subjects variance. Yeah, between subjects variability. So some of these variations between subjects are nested within the effects in interactions, right? We said subject, we're going to nest it inside of Q and list. And we see, okay, we've got some of the variations. We have subject Q, that's one of the variations. We have subject list, this is another one of the variations. And we have subject Q list, that's another variation. So some of the variations between subjects have been nested inside of the effects, right? We've got our effects here and the interaction here. Not all of it. Not all of it. We still have part of it up here. Right? This was the part that we were throwing out. This is the part that we were saying, okay, you know, I don't want to know how fast a person is overall, or how slow they are overall, or how good their memory is overall. What I'm really interested in learning about is how these different factors affect people in general's memory, right? So let's get rid of that variability that's just due to the individual variations that aren't related to these effects in interactions. So in the repeated measures ANOVA, we took that and we basically threw it out. It doesn't contribute to any of these things. It's by itself. It's independent. Okay, now let's do our 2x2x2 mixed ANOVA. 2x2x2? I have three variables, three factors, right? Q, list, sex, right? We have 2 levels of Q, Q or not. We have 2 levels of list, abstract or concrete. We have 2 levels of sex, male or female, right? So we have parts that are like a regular ANOVA. Which part is like a regular ANOVA? Sex. Sex is like the regular ANOVA, right? It's something that varies between subjects. We also have parts that are like repeated measures ANOVA. Q and those. Perfect. So how do we mix these parts to get a mixed ANOVA? This is a hypothetical question. I don't want you to answer this. You can think about it. Don't answer it because I don't want to confuse people too much with wrong answer. So let's just get into what it is. Let's do the easy parts of this. So the easiest parts of this have to do with the sums of squares and the degrees of freedom for the factors that we're interested in, or the interactions of the factors that we're interested in. So degrees of freedom for our effects. How do we figure out the degrees of freedom for an effect?
Minus 1.
What minus 1?
2 minus
K minus 1. K is the number of levels. So for a particular variable. So if we're talking about main effects, the degrees of freedom is just the number of levels for the factor that we're talking about, minus 1. So what's the degrees of freedom that we have for our main effect of Q?
1.
1. We have 2 levels, right? Cubed or not cubed, minus 1. How many degrees of freedom do we have for our main effect of list? 1. How many degrees of freedom do we have for our main effect of sex? 1. Easy. Okay. So calculating the main effect degrees of freedom, no problem. The main effect sum of squares. How do you get this? We already know how to do this too. We subtract the grand mean from the mean for each level of that factor, right? So we've got a difference between the mean of the factor, the mean of the level of the factor, and the grand mean. Then what do we do with those differences? Square them. Add them up.
Divide by
Numbers.
This is the sum of squares, not mean squares. Do I have mean squares up here? No. Sum of squares. We're not going to divide by anything for sum of squares. We're going to multiply by something. We don't divide by n.
n minus 1.
Multiply by n minus 1. What's n?
Number of levels.
Not number of levels.
Observation.
Okay, number of observations for what? Total?
No.
No. The number of observations that you have for each level of that factor. Okay. Subtract the grand mean from the mean of each level. Sum square differences. Multiply the number of observations for each level. This apparently was a big pain in the butt on the homework. I was like, oh, the students are going to love this. This is going to be easy. Oh well, it wasn't. So let's do a quick review on how to figure out what you need to multiply this by. Okay? So, finding the multiplier. In order to find what we need to multiply by, if we want the number of observations for each level, what we can do is find the total number of observations and divide by the number of levels that we have. Right? So, find the total number of observations. You can do this by saying length, dv, or you could do this differently. So, like on some of the questions I said, you have a 2x3 ANOVA with 8 observations per condition. Well, if you have a 2x3, then you have 6 conditions times the 8 observations per condition gives you 48 total observations, right? You don't have to use R to figure this out. You can use your brain to figure it out too. And then all you need to do is divide by the number of levels for the factor of interest. You can do this in R, or you can just look. If I say a 2x3, or a 6x7, or whatever the numbers are, if you want that first piece, you just divide by that first piece, that number that represents that first factor. So, that's it. Yeah. Yes. Okay, did you have a question?
We have 2 by 4 by 2.
So you've got a 2 by 4 by 2. All right, we can do an example of this. All right, so we have a 2 by 4 by 2. 2 by 4 by 2.
You want to calculate this one? The first one, let's say the 2 levels one.
Okay?
And which one would you multiply by? Which number you might multiply?
How many observations do I have per condition?
8.
8. I have 8 observations per condition. So this is my ANOVA. There's a description of what my ANOVA is like. So we have 3 factors with 2, 4, and 2 levels. And we have 8 observations per condition. So we have 2 times 4, that's 8 times 16. 16 conditions. And we have 8 observations per condition. So that is 128. So we have 128 total observations. If we want to know the number of observations for each level, we divide by the levels for the factor that we're talking about. So if we divide this by 2, 128. It's weird. So in America, we divide like this. And my kids, like they were doing something like this.
No.
I don't I got it. I'm like, what? How do you do this? Okay, anyway, you don't have to use either way. Okay. And then, so 128 divided, we'll do it this way, by 2, 64. Right? Pow! You've got it. How about for the second factor? Well, you want the second factor.
Divided by 4.
That's 32. You want the interaction between the first and the second factor?
8.
You're going to divide by 8. Because you have 8 combinations, right? You divide by 8, now you've got, is that 16? And then all of a sudden the homework is chocolate.
So, what is 16 now? What will we do with 16?
You multiply it by that sum of squares that you found.
This is for total sum of squares?
No, this 16 would be the sum of squares for the interaction. Here we were just talking about the main effect. So we haven't gotten to interactions yet.
We just the first one.
Yeah. Okay, so like the sums of squares and degrees of freedom for the main effects, we also calculate the sums of squares and degrees of freedom for the interactions the same way we always have. So there's nothing new. So the interaction degrees of freedom, so we had Q by list by sex. How many degrees of freedom do we have for the interaction? 1. How do you figure that out? People come to my office and they say things like 5 or 6. How did you figure out 1?
Each of them is 2 and subtract 1. So 1 multiplied 1 multiplied 1.
Right. So in order to find the degrees of freedom for an interaction, all you have to do is multiply the degrees of freedom for each of the factors that's in that interaction. So you have 3 factors, Q, list, and sex. Each of those had 1 degree of freedom. So if you multiply 1 times 1 times 1, you get 1. It's interesting. The degrees of... First, let me preface and say you should not cheat. You should not falsify data. You should not plagiarize or do things like this. But a common way that a teacher can figure out if a student has faked an analysis, like if they have to do a research project and then do some analyses and then report the results, is if they report the wrong degrees of freedom. Because the person reading the paper can figure out what the degrees of freedom should be for themselves. They know how many subjects they know how many conditions there are. you can calculate the degrees of freedom. And students that really don't understand what the degrees of freedom are, they'll just make up something that looks right. Oh yeah, you have a small one for the first thing, and you have a big one for the second thing. So let's see, F1, and we'll say 5, that looks right. But a good statistics person will know that's wrong. You should have 1 degree of freedom
Why?
for the interaction.
No.
Or, actually, that's error, that's different. That's exactly right. I'm trying to figure out a way how to like fix it. So, what it should have been was something like F5, let's say 16, and it should really be 1. And this probably should be something else too. We can figure out what the 16 is. All right, we'll figure out what this part should be in a tab. Okay, so the interaction degrees of freedom, we just multiply the degrees of freedom for the individual factors. So we've got the interaction sum of squares. How do we get it? Again, we're going to subtract the grand mean from
Mean of level.
the group mean. Yeah, the different combinations of the levels, right? Of the factors that are involved. So we're going to subtract the grand mean from the mean for each combination of levels from the interacting factors, sum the square differences, multiply by the number of observations for each combination of levels, or for each group. And then, is that it?
Divide.
No dividing.
Add.
No adding.
Subtract.
Subtract. We're going to subtract all of the sums of squares for the effects that are involved, and also for the lower order interactions of the factors that are involved in the interaction of interest. All right, we've done that before. This is the same thing here. Cool. Finding the multiplier, again, for the interaction, we want the number of observations for each combination of levels. We need to find the total number of observations. We've already talked about that. And we need to divide by the number of combinations of levels for the factors of interest. That's just the number of levels that is indicated here. So you want the interaction for the first 2. So we had 2 times 4 times 2 times 8, so there are 128 total, right? 2 times 4, this will give us the number of combinations that there are. So we've got 8, so we divide 128 by 8, and we get, I believe that was 16, right?
But in this case, what are we doing exactly the 2 by 2 by 2 or just 2 by 2?
For this example, this was from the homework, it's one that we got.
I'm saying for the slides.
It depends which interaction you want.
I mean,
So we said we have a 2 by 2 by 2. Give me an interaction out of that. So are you talking about the interaction between Q and list, between list and sex, or by Q, list, and sex?
I mean, how can we differentiate between the mixed interactions? Because we have dependent and independent, and we have.
So we've talked about calculating these for our non-repeated measures ANOVAs and for our repeated measures ANOVAs. And you're wondering, our mixed ANOVAs, these are different, right? Actually, do I say it's the same here? Yes. Calculate the degrees of freedom and sum of squares for our interactions just like we always do. So there is no difference between finding the sums of squares or the degrees of freedom for non-repeated measures ANOVA, for a repeated measures ANOVA, or for a mixed ANOVA.
But in the repeated measures, we include the subject.
For the repeated measures ANOVA, we included the subject. That's right. So if I'm going to qualify this, let's say the sum of squares and the degrees of freedom for our interactions involving the factors we're interested in is just like it always was. Subject we're not interested in. So these are for the things we're interested in. We'll get to the subjects in a minute. Because that is different. That is different. But for everything else, it's the same. And in fact, once you find the degrees of freedom for the subjects, you know how to calculate the degrees of freedom for the interaction involving subjects. You just multiply the degrees of freedom of the subjects by the degrees of freedom of the other things. And you got it. Okay? All right. So, on to the last easy. Last class we said that we could treat subjects like a fact, right? And that's still true. We can treat subjects like a fact. For our repeated measures ANOVA, the only thing that varied between subjects was the subjects. Right? So you have one subject getting a concrete list with no Q, a concrete list with a Q, an abstract list with no Q, and an abstract list with Q, right? So Q and list varied within subjects. The only things that varied between subjects were the individual subjects. No? No. Why? What's wrong with that? He's actually wrong. So don't get confused when he says, no, he's wrong.
No, I didn't understand it.
Huh, no, you don't understand it. Let's go on to the non-repeated measures of ANOVA. Maybe this will make more sense. We'll go on, come back. Okay? So for the mixed, down here, for the non-repeated measures of ANOVA, we have at least one factor of interest that is varying between subjects. So this would be like one subject gets abstract queued list, a different subject gets an abstract unqueued list, a different subject gets a concrete queued list, and a different subject gets a concrete unqueued list, right? So lists and queues are varying between subjects. Subjects also vary between subjects, right? Are you different from me? We're different subjects, right? Subject 1 varies from subject 2. I'm older. I'm American. Right? We differ from each other. So, not only for this, we have Q differing between subject, we have list differing between subject. We also have the subjects differing between each other. Okay? So now if we go back up here, we have one subject. Each subject gets each combination of Q and list. So Q and list, it's not varying between subjects. It's varying within the subjects. The only thing that's varying between subjects are the subjects. Right? I get all of those combinations. You also get all of those combinations. Did we get different combinations? No. So the combinations that we get doesn't vary across subjects. What varies across subjects? The subjects do. I'm different, you're different, she's different, the other person's different, right? So that's what I'm saying when I said here. The only thing that varied between subjects was the subjects themselves.
So varied means being different.
Yes. Otherwise, you would have a constant. Same subject, every condition. If you did the same subject in every condition and you only use one subject, then you have nothing that varies between subjects. It's a single case study, right? All right. So, so for a mixed ANOVA now, we have at least one factor of interest that varies between subjects. So Q and list, each subject gets every combination of Q and list, right? I get the same combination, you get the same combination, she gets the same combination, he gets the same combination, right? So Q and list, everyone's getting the same. However, not everyone is the same sex. I'm a male, she's a female. He's a male, she's a female. That is differing between the subjects. One group of subjects is male, one group of subjects is female. That's a difference between subjects, right? So for the mixed ANOVA, we have at least one factor of interest. I guess you could say we have at least two factors of interest. One is the subject itself, and then that other thing. Here it's sex. All right. Does that make sense?
Yes, yes.
No? Yes? I think. Okay, repeated measures experiment. Do you get different conditions than she does? Yes. With repeated measures, everyone that's participating gets the same conditions.
Yeah.
The simplest example of this would be like the paired t-test, right? I participate in one situation, I participate in the other situation, I subtract myself out. I'm left with the difference, right? So the conditions, you are each getting the same conditions. You're getting the same conditions as she is, as she is, as she is, as he is, as I am. Everyone's getting the same conditions. This means that the conditions, they don't differ. No one has a different set of conditions than anyone else. When something doesn't differ, it's a constant. It doesn't vary. Does that make sense? So I have the same set of conditions that you do. So the conditions aren't varying between subjects. I have the same condition that you do. However, the conditions do vary within a subject. I participate at time 1, I participate at time 2. Well, time 1 is different than time 2. You also had time 1 and time 2. Each of us, time 1 is different than time 2. Right? So those conditions are varying not between us, but inside of us. Oh, yes?
So what will we include by having two factors varying between subjects? Error term?
Can you repeat the question? What do we have when what error term?
Would be induced when we have like two factors, one between subjects.
Okay?
So what that means?
I still don't understand it. So we have two factors. And what will the two factors lead us to? Well, so what we're trying to do when we have multiple factors in some dependent variable, we're trying to determine if either of the factors has an effect on the dependent variable, or if there is an interaction between the two factors that affects the dependent variable. We are asking basically the same questions regardless of what type of factors we have. Does sex affect your score? That's basically the same as saying, does a Q affect your score? It's a different variable, but it's still basically the same question. Q was Q was repeated measures, so that's something that's varying within a subject. And sex was not repeated measures. Sex is something that's varying between subjects. But we're still asking the same question. Does this factor affect that? Right? And the same thing with the interaction. Does the interaction between this factor and that factor affect this? Doesn't matter what the factors are. Between, within, no problem. Okay. Okay, so down at the bottom we said for non-repeated measures ANOVA we had at least one factor of interest that is varying between subjects. So let's take another look at our non-repeated measures ANOVA. Remember last class we said for a non-repeated measures ANOVA the sum of the squares of the subject was the same thing as the total sum of squares? We did that. I said model the response or the scores off of subject B. In subject B, there was one subject for each observation. And that just gave us one thing. One thing. And then we said, okay, Now let's throw in these other things. And we saw that when we threw in those other things, we were able to break that big sum of squares up into different pieces, right? Into independent pieces. So for non-repeated measures ANOVA, the sum of squares for the subject was the same thing as the sum of squares total. To get the sum of squares for the factors that vary between the subjects and the error term that we were going to use, all we did was break up that sum of squares. Took the total sum of squares and broke it up into pieces, right? By doing exactly what we've talked about. By subtracting the grand mean from some other means and squaring those differences and adding them up and multiplying them appropriately. That's how we did it, right? So to get the degrees of freedom for the factors that vary between subjects and the single error term, we broke up the degrees of freedom for the subjects, which is really just the degrees of freedom total, right? For our non-repeated measures ANOVA, and broke that up into pieces. Because the degrees of freedom for all of those pieces add up to the total degrees of freedom, which adds up to n, if you consider n being the total number of observations that you have minus 1. Exactly. So, all we need to do for our mixed ANOVA, we have a whole bunch of pieces, right? We had, let me go back if I can. Here. We had a whole bunch of pieces, right? And we said that this piece was like the sum of squares for the subjects, right? Now before, when we just had a one-way ANOVA, the sum of squares for our subjects was the sum of squares total. And when we wanted to find out the degrees of freedom and the sums of squares for the different between subjects factors, all we had to do was break up this sum of squares appropriately. So that's exactly what we're going to do in the mixed ANOVA. We are going to break this part up into pieces. We'll also end up breaking these parts into pieces too, the error terms. All right, so let's do it. Okay, so if we do the repeated measures component by itself, it will give us the sum of squares and degrees of freedom for the subjects. This is exactly what I just went back to. So the error subject here, we have this many sums of squares, 3 degrees of freedom. Which makes sense. We have 4 subjects. 4 subjects. 3 degrees of freedom for subjects, right? Cool. Now, we have one between subjects factors with 2 levels, right? Sex. Sex is something that varies between subjects. How many degrees of freedom does sex have? 1. So if we are going to break this up into pieces, if this is like the sum of squares total for the for the non-repeated measures ANOVA, and we're going to break this up for all of the between subjects factors, or the between subjects interactions, then one of those degrees of freedom is going to go to sex, which will leave us with how many degrees of freedom for subjects left over? 2, right? Did you have a question, Steve?
I was asked for the formula. I was talking like, why would we first add subject plus Q and this interaction?
So let me reset the camera and then I'll answer. Okay, so last class I built a model that was a little bit different from this. It said scores is modeled by subject plus Q times list plus error subject nested within Q times list. Like that, right? If you got my email, so I sent an email out. I made a silly mistake. So in preparing for the class, like I start with one slide and then I copy and I paste. And then I edit, so I don't have to keep rewriting everything again and again. And I copied earlier in the class we did something where we got the subject to pull the subject out, and I left it in. Now, if you're doing a repeated measures ANOVA, if you leave this in, you will still get the same values for everything that is important that you're interested in doing. However, when you do the mixed ANOVA, this will actually screw you up. So for last class, this technically didn't give us the wrong answer, but we can simplify it, get rid of this, just have that, and we are good to go.
Can you explain more? So we labeled the subject with residuals.
Right. So subject now is labeled as residuals instead of subject.
What does that have to do with the mixed? No, how is that affected?
How will that affect it? Let's answer this at the end of class, because this isn't something that I want you guys to learn necessarily, because how it affects, how misspecifying the model gives us the wrong answer. You already have enough to learn, how to do it the right way. So showing you why it's wrong and how it is wrong, if we have time at the end, I'll do it. All right? Okay, so we have our better model, uncopied and pasted. Actually, this is copied and pasted. You see the spacing here? In R, normally I don't do that. That comes from copy and paste. Okay, so we have one between subject factors with 2 levels, so we're going to take 1 of the degrees of freedom away from this. And also part of our sum of squares will also go to that. Calculate the sum of squares just like we would any other sum of squares by subtracting the appropriate means and multiplying by the appropriate things and squaring and summing everything up. Okay, so degrees of freedom for the interaction between Q and list and the error. So let's figure out how many degrees of freedom we should have for our Q by list interaction. 1. Good grief, that was easy, right? You have 1 times 1, 1, right? Now for the error. It's not df Q list, it's the degrees of freedom for subject times Q times list. 3. 2. 2. We have 4 subjects. Minus 1, which gave us our total subjects' degrees of freedom, but we have 1 between subject factor. It has 2 degrees of, it has 2 levels, so it has 1 degree of freedom. So we're going to take 1 of those degrees of freedom from subjects away. We are left with 2. So those of you who said 2 are right. Because just like in our one-way ANOVA, right? If we had a one-way ANOVA with 16 subjects and 1 factor of sex, so we were just doing memory scores for males and females only, right? So we have 16 subjects. We have 1 between subject factor, say BS between subject, sex, 2 levels. So how many degrees of freedom total do we have? 15, right? Degrees of freedom total equals 16 minus 1, that's 15. How many degrees of freedom for our subjects do we have? For our subjects. So before we said the subjects is the degrees of freedom total, right? But what do we do to the degrees of freedom total? We subtract the different parts from it, right? So for degrees of freedom for sex, we have 1, and the degrees of freedom that we have left over for the subjects, which is serving as our error, we have 14, right? So you may have seen me go like subjects. That's why I did the subjects. It's the error. All right. So 2 was exactly right for the error. Let's have R do the heavy lifting for us. This is going to be so easy, your mind is just going to be blown. If you already know how to specify the model for the repeated measures. So, for the repeated measures ANOVA, let's specify a general model for repeated measures ANOVA.
Do you want to use multiplied by V2? Multiplied by whatever factors we have, plus error. Nested by these.
Okay. Right?
But in the first we just make that redundant. Okay? And this is close.
Right? So that's our general model. We can just say dV is a function of the factors of interest plus some error where we have subjects nested within something. Let's just leave it at something for right now. For the repeated measures, it was the factors of interest. But now we're talking about a mixed. So that something will be different. Let's see what it is. Boom, here it is. So our degrees of freedom is modeled by all the factors of interest. That's exactly what we wrote up there before. By all the factors of interest, plus error, which was our subjects nested within something. All the within subject factors of interest, you could say.
Are you subjective humans?
No, within subjects. Within, it's just
Okay.
putting the word together, no subtraction. All the factors of interest that vary within subjects.
So we want to write 6 here.
Yes. So we will write the sex in the beginning, but not in the list.
We will write sex in the beginning, but not in the list. Let's see. Yes! That's it. Summary, AOV, scores as a function of sex times Q times list, plus the error, which is subject, nested in Q and list. So this actually is the same thing as the formula for a fully repeated measures ANOVA. Why? Because in a fully repeated measures ANOVA, all of the factors of interest are factors that are varying within subjects. So you only need to know one model for mixed or repeated measures ANOVA. This is it. If you know that, you can do both problems. All right, so that's exactly right. So you got it. Here it is. Okay. What do we have? Well, we have a lot of stuff. We have degrees of freedom. So this is for the effect of sex. We have degrees of freedom for the error, which is related to that subject, what's left over of it. We've got the sum of squares for those pieces. We can calculate the mean squares of those pieces and get the F value of those pieces. So up here, where you just have the error for subject, Imagine that we didn't have sex only. We had sex and ethnicity, and whether or not you like coconut. So then you would have up here all of those varied between subjects, right? In a one-way ANOVA, everything that varied between subjects, you had one error term for. Now, we can't actually have the coverage and ethnicity and all those other things up here because we don't have enough degrees of freedom left away to give. We would need to have more subjects if we wanted to do that. But if we did have more, we would have a single residual and we could have one line for sex, one line for ethnicity, one line for whether or not you like coconut, one line for the interaction between sex and ethnicity, one line for the interaction between sex and whether you like coconut, and all of the other interactions of the between subjects factors. Yes?
So we have like, the residual will go actually 2 if we have 3 levels in one of the factors.
Yes, if let's say we had this happens sometimes. People, they give out surveys. Please indicate whether you're male or female. Sometimes people don't indicate anything. That's actually usable data. You can use that. You have people that identify as male, and people that identify as female, and people that don't identify as either. Right? There could be a difference between that. So he's absolutely right. If sex was male, female, or blank, we would have 2 degrees of freedom for sex. This would be 2, this would be 1. Because we're taking those degrees of freedom, the between subjects degrees of freedom, away from the total between subjects degrees of freedom that we have. Okay. We also have our F's for our main effect of Q and any interactions of Q with between subject factors. So we have Q. We also have the interaction of our between subject factors, sex, with Q. If we also had coconut, we would have another line for coconut and Q. And then we would also have a line for sex, coconut, and Q. Because the sex and the coconut liking are things that vary between subjects. So you'll have the one thing, the within subject factor, and all of the interactions with that within subject factor with all of the between subject factors. We will have a single residual for each of those. Same thing for the effect of list. And then finally, for our interaction, we have the F's for the interaction of Q and list, and any interactions of this interaction with any of the between subject factors. Here we only have one, sex. So we have the Q and list interaction, the sex, Q, and list interaction, and then the residuals, which is like the subject, Q, list, right? Cool. Sweet. So let's compare these really quick. So this is for our fully repeated measures, ANOVA, ignoring sex. Now, on top of this, I'm going to put the mixed ANOVA that includes sex, right? There's no sex here, we have sex here. This is our RM, this is our mixed. Look at this. Here, for this first term, we had 3 degrees of freedom. We broke this up into 1 and 2. We had 4,329. Let's see if these add up. Is that, am I adding right?
4.
Yes, right. Same thing?
Yeah.
All we've done is we've taken this part and broken it up, just like we had been doing in our non-repeated measures and ANOVAs. And if you look down here, the residuals here, this error part that previously was just about subjects. Now we have subjects and sex, so we are breaking this up. We had 3, now we have 1 and 2. We had 363, now we have 363. Same thing down here, right? 3, now we have 1 and 2. 7, 7, oh, am I doing that right? 207.7. Yes! We're just breaking up the residuals appropriately. And same thing down the bottom. That's it. Chocolate. Now, the problem, maybe before we talk about the problem, are there any questions? When we say, let's say we had the function of subject plus all of this stuff, subject plus all of this stuff, right? This was your question earlier about like how this is going to affect things. Well, what's going to happen is you are saying treat subject as its own factor. And so when you treat subjects as its own factor, all of this we said was due to subjects, right? Now, if we treat subjects as its own factor that we are measuring in its own right, that we want to test and maybe see if it's different, if there's an effect or something, then what we are doing is we are taking that error and we are setting it aside, and we're not going to be able to take things from it. But by treating this as an error, as a total of something else, then we can break it up into pieces. And that's a short version. So, let's build some models. Because that's what you're going to have to do on the test. You're going to have to build a model. So, you have a one-way ANOVA for the factor of favorite soccer team. And there are 4 options. There's Besiktas, which is the best option. We have Galatasaray, Gala, and we have Trabzonspor. And we have everyone else. No, Fenerbahce fits in with everyone else. Fenerbahce çok kötü, yeah? Okay. We have some dependent variable, say coolness factor, or not coolness factor, coolness score, coolness, right? This is our independent variable, soccer, and we have our dependent variable, which is coolness. So we're going to get, let's say, 6 Besiktas fans, 6 Galatasaray fans, 6 Trabzonspor fans, and 6 fans of who cares what the other teams are. So we will have how many total subjects? We have 24 total subjects. 24 total subjects. And we're going to measure how cool they are. We're going to have them take this test and see how many of the answers they get right in a cool way somehow. This would be hard to figure out like how you build this, but you can do it. Okay, so we get the coolness scores, and now we want to do an ANOVA. How do we specify the ANOVA? AOV.
Coolness.
Coolness.
What's this? Yes. For one ANOVA, which factors?
There's only one.
Factor.
For some of these things, like all of the information that is provided is not necessarily necessary to get the right answer. It doesn't matter how many different levels that you have here. It actually doesn't matter how many subjects we have here either. It's the same model. If I ask you about other things like degrees of freedom for soccer, then that's important. important. We have 3 degrees of freedom for soccer. Yeah.
If we have different vectors.
What if we have different factors? So we will have now, so this is between subjects. This is a between subjects factor. Now let's have a within subjects factor. So an IB, have you had my class? Actually, that's not a within subjects factor. Correct? That's another between subjects factor. Right? So you've either had my class or not. So we need to come up with some within subject factor. What could be our within subject factor?
Watch the game. Did you watch the game? Yes or no?
Is that a within subject factor? That's a between subject factor if you watch some game, right?
It's the same guy. Watch and didn't watch.
Right, but like I watched it, she didn't watch it.
Okay.
Right? We could use sex, but sex is also between.
Playing before. Playing before.
Have you played before in one of them? That would also be between. Okay, here's the within. I'm going to measure how cool you are before I show you a Beşiktaş football match. And then I will measure you after I show you a Beşiktaş football match. Okay? So our within will be, have you seen? Okay, watched. But we're measuring it twice. Before and after. Within. Okay, so now we want our mixed ANOVA. What is it?
You don't want the mixed ANOVA. I just want the factor of soccer.
You just wanted what?
The soccer factor.
The soccer factor.
One way. But we have different factors.
That was this.
Is it the same again if we have different factors?
If you have different factors, you won't have a one-way ANOVA anymore. Or maybe you will. If you have soccer and any other factors, it's not a one-way ANOVA anymore.
Yeah, but you want us to find what does the soccer by itself indicate.
Right. Is if you want to find out what soccer by itself indicates without any other factors, this is what you use. If you are interested in other factors, then you need to specify those things in your mind. So now we have more factors. So we're going to have a new model. So what is our new model? It starts like it did before.
Soccer multiplied by, that's
Say now.
multiplied by which?
I watched. Okay.
Plus error.
Plus error. Subject. Nested.
By only watch.
Why only watch?
By only watch. Why only watch?
Soccer and net.
Soccer and nap, he says. Or she says. They both say soccer and nap. He says only watched. One, I just gave the answer away. One of them is correct.
Because we said if we do not use within subject in the error.
It's not that we are not using within subject factors in the error term. We are only using within subject factors in the error term for the nesting. Right? If we go back, all within subject factors. This is a between subject factors, if you had my class or not. This is a between subject factor. Some people like Beşiktaş, and there are other types of people too. This is a within subject factor.
That's subject. Just watch. Okay, that's true.
Watch. He was right. That's it. That's all. Next class, our next regular class, we have an exam. Friday we will have a review. Come Friday.